Hello everyone, this is Sagar Malum. As a senior project manager from Ecosmob, I am here to cover a very interesting topic. As you can see on the screen, I am going to talk about optimizing networking for RTC apps. And here we are going to harness the power of OpenSIPS and Calico. So moving on to the next slide. So over here you can see I have noted down some of the challenges which comes across us when you are dealing with Kubernetes and RTC altogether. Some of the challenges are common. It is not specific to RTC, but like most of this which is related to networking, those are very important when it comes to an RTC application. So if you want to run an RTC app on top of Kubernetes, you need to consider these challenges and try to optimize the network as much as you can. So first one is network latency. As you know that RTC is the real-time communication. So there should be zero latency. Basically an RTC app cannot tolerate even a 1 second or 1 millisecond of latency. Second thing is complexity in the network configuration. The orchestration of the RTC app is quite complicated, and usually you will have multiple media servers and multiple SIP servers, and most of the time you need to do deep packet inspection and then route the traffic across various servers or pods or any other components which are part of the Kubernetes. So which is again additional complexity which comes with this combo. Resource allocation and the isolation. So this is more of kind of generic problem. Like as you know that Kubernetes allocates the resources at the pod level, and it is very difficult for us to identify ahead of time what should be the resource allocation for a particular pod. You need to do some benchmarking for that and then come up with the numbers. Then observability and alerting. So like one of the best features of Kubernetes is that you can run thousands of pods, basically thousands of applications. All of them can be orchestrated by a single click. But with those 1,000 pods, the big challenge comes is observability and alerting. So how are you going to monitor that? How are you going to observe that? And how are you going to get alerts? Like there are thousands of pods, so the alerting has to be very specific, the monitoring has to be very accurate and fast. So that is another challenge. Then handling of the stateful sessions. So like you can take an example of an RTC application hosting a conference, and due to some reason that application crashes. So when the another pod or another instance of the application starts, it should be stateful. It should start from where the previous one left. So that is the fifth one. And finally, UDP traffic management. So RTC is all about UDP. And with Kubernetes, it comes by default with the overlay networks. There is a lot of layers of networking, so you need to make sure that you minimize layering and thereby try to manage UDP traffic, because there will be thousands and millions of packets which are going through the wire at the same time. So yeah, these were the challenges, and I wanted to discuss these challenges so that I can propose the solution and how I used Calico and how I used OpenSIPS to solve all these problems. So before we talk about Calico and OpenSIPS, let's talk about underlay networks. This is something very basics. I want to cover this because it will help us understand what kind of problem Calico and OpenSIPS solves for us. So underlay network, what is underlay network? It is as simple as it can be. It is hardware orchestrated, minimal amount of layers, very less overhead and very fast. But again, there are cons. So I have noted down cons over here because pros everyone knows, right? So hardware orchestrated. So everything is based on hardware. So if you want to do a lot of fancy things, it's very tough. Second thing is that with Kubernetes, a single host, a single machine can host multiple pods, which means that it may require multiple number of IPs at the same time. So which is very difficult with this, because you need to insert a Ethernet port for each and every IP. So these are the two main cons. There are some other cons, but I for the RTC app there are a lot of advantages for the underlay network. Now overlay network. So this is as you can see in the diagram that it is something which runs on top of the underlay network, and mostly Kubernetes comes by default with this. Some of the advantages of this is that you can have n number of IPs, you can create your own virtual network. So the problem of hardware orchestrated underlay network is quite solid over here. But again, it comes with other cons. Like for example, there is additional processing required. So like I mentioned that there is a latency issues, right? So the more number of layers, more processing, and thereby there is a chances of there will be latency when packet reaches from one particular port to another particular port, etc. And next is cross subnet routing, which can become very, very complicated. I don't think that underlay network behaves better with this, but in case of overlay network, it just becomes more and more complex. So what we need to do here, that we need to find something which has advantages of underlay network as well as overlay network, and that's where Calico comes very, very handy. So moving on to Calico. So what is Calico? So Calico is a CNI plugin. There are a lot of CNI plugins available. Calico is the one that I have used, and I found it extremely useful. Some of its salient features are cross subnet overlays, BGP support, non-clustered node support, which is, like I would say, a kind of salient and exclusive feature of Calico. And it is compatible with all the popular CNI plugins like Amazon, VPC, and Azure and Google Cloud provider. Calico comes with two modes, like we talked about, right? That once there is overlay mode and then there is underlay mode. So overlay mode is what I already explained. I will not dive in deeper into that because I want to focus more on the underlay network and the problem that Calico solves. So, but there are two ways to implement overlay network. One is IP to IP and VXLAN. And underlay network is the BGP peering mode. So here we are going to use border gateway protocol in order to implement the network and the routing. So moving on, so I'm moving on to this diagram. So initially you may see like there is a lot of information over here, but I'll try to simplify. I'll first explain that how this diagram looks and whatever you see, what does it mean. Okay, so I'm assuming that all of you are familiar with basics of the Kubernetes. Like in Kubernetes, there are worker nodes, and on top of worker nodes, you can have like one or more pods, and that is what I have like shown over here. So you can see that there is a worker node A and there is worker node B. There is also one non-cluster node. So this is something which comes exclusively with Calico, which I wanted to cover in this. So that's why I also included this. So here you can see that worker node A, which has the main IP, right, which is 1057.7, and worker node B, which is 1057.8. So now these IPs are assigned by the underlay network. So here you can see there is a gateway which has the like 10.57.1, and it is an underlay network. And through Ethernet ports, these fixed IPs are allocated. Now, how Calico operates the network? That is what I am going to explain over here. So when you configure Calico plugin with Kubernetes, what it does is that it will actually assign a set of virtual IPs to each and every worker node. So here you can see that, like for this example, you can see the port IP range assigned to worker node A, it is 10.132.0. So 64 IPs comes under this CIDR. And the worker node B also has 64 IPs, but its range is different, like 10.133.0. And whenever any pod spins up on this particular worker node, it gets one of the IP assigned from this range. And all of this is managed by Calico. We don't have to worry about it. Calico just does it out of the box. Another interesting thing to note, I think it is very important thing, that when you spin up a pod with Calico CNI, it also creates a virtual interface. So that is what I have shown over here and here as well. So here you can see that this is the underlay network port, and you can say this is kind of overlay network port. It is not 100% overlay, but you can just assume that it is an overlay conceptually because of using BGP protocol. Like a lot of disadvantages of overlay network are kind of overcome over here. So for each and every port, it will just create one interface, and that's how it routes the packets from another node straight to the pod. So here you can see that Cali1 is pointing to pod B1 and Cali2 is pointing to pod B2. And over there you can see that Cali1, the same name is pointing to different pod, which is pod A1, but it's a different worker nodes and it is a different IP range, so it's not a problem. Same thing for the Cali2. And you can also see the IPs which are assigned to a particular pod. So now the interesting thing to see over here is the routes. So all the magic is done here. Here you can see that there are, these are actually network routes. I am sure all of you are familiar with that. But I'll just tell basics of it. What does it mean? That if you want to reach to this destination, you need to go through this particular IP kind of a hop. And to go to that hop, you need to use this particular interface. Okay, so let's say that now any particular packet wants to reach to worker node A. So here you can see that 0.0.0 and 10.57.1 ETH0. So it will be sent from here and here to here. Okay. Same way, let's say that this worker node wants to go to the non-cluster node. So same thing, like there is a 10.50.7. So it will go from here and from here to the non-cluster node. Now, interesting thing to see over here, it is how the routing of the pods which belong to the same worker node and the pods which belong to the different worker node are created. So let's take an example of this one, 10.1.32.0. Okay, so this is the IP range which is assigned to worker node A. Okay, and I can see there are two pods, 10.1.32.1 and 10.1.32.2. So now let's say that if any packet wants to go to this particular node, what it will do, that it will see, okay, I want to go here, and from here there is this particular gateway. Sorry, actually I was referring to this route, my mistake. So for 10.1.30.0, it will go to this particular gateway, and what is this? This is the fixed IP of a worker node A. So from here it will be sent out to here, and through this interface it will be going out and reaching over here. And let's say that it wants to reach to 10.1.32.1. So when this packet will reach over here, like you can see over here, that let's say that pod B1 wants to reach to pod A1. Okay, for example. So what will happen, that a packet will go out from here and it will be going through the gateway to ETH0, and then ETH0 will look at the routes. Okay, so 10.1.32.1, it is assigned to Cali1. And what is Cali1? It is this interface. So from there it will be directly sent to the pod A1. So here you can imagine how we have minimized the additional layers in case of overlay networks, like we discussed, right? There are IP to IP encapsulation, and this is like encoded and then decoded, and all the CPU power is required. It also like impacts the size and network latencies. So here we have actually implemented underlay network, and which has advantages of an overlay network. And one good thing over here, that look at the non-cluster node. Let's say there is a non-cluster node who wants to reach to a particular pod. So Calico also manages the routes for that as well. So here you can see that this range 10.1.32.0, which is worker node A, and 10.1.33.0, which is worker node B, it is assigned to ETH0, and these are the fixed IPs assigned over there. So basically, without having any kind of additional layers of an overlay network, each and every node can directly reach to the other node without any kind of additional layers, any kind of complexities. So this is huge when it comes to RTC applications, because we have almost eliminated 2 to 3 layers, and because it is BGP, it is easily extensible. You can also extend it over the internet, and you can also add multiple number of nodes over here. So yeah, this is it. Like a lot of things has been covered in this single slide, and I hope you guys understood how Calico solves the networking overhead by implementing BGP to peer mode. So moving on to the next thing from here. So I covered first thing, like Calico power, right? Like here I showed that how Calico can solve this particular problem. That was the first part of this presentation. Now the second part of this presentation, which is OpenSIPS. Like how did I utilize OpenSIPS to further improve the networking and to like optimize the networking. Alright, so now moving on to the next slide. So in the previous slide, I have covered one part of the presentation, like how we can use Calico to optimize the networking, like eliminating the additional layers. And now I'm going to cover the second part of the presentation, which is how I used OpenSIPS, how I harnessed OpenSIPS to improve the networking and like optimize networking in general. So before we talk about that, I just want to again, I want to come to basics. I want to explain what are the Ingress and the Ingress controllers, so that it is easy to understand how OpenSIPS adds the value over here. So Ingress and Ingress controllers, as you know, that Kubernetes is a closed network, right? If you want to send traffic to the internet, or you want to receive the traffic from the internet, you need to do something about it, and that's where Ingress controllers comes into the picture. What it does is that it basically controls the Ingress traffic. So anything which wants to come into the Kubernetes cluster, here you can see there is a Kubernetes cluster. There are pods, services, and also there is an Ingress endpoint over here. And this is an Ingress controller. So in this example, I have used generic and most widely used Ingress controller, which is Nginx. So the way it works is that Nginx Ingress controller will integrate with the Ingress endpoint of the Kubernetes, and whenever any routing changes are done, okay, basically you can create a service and you can define the routing policies. Like for example, here you can see there is a cluster IP service which is created. So the request will come over here and it will be routed to the service, and depending on the cluster IP, it will be routed to the particular pod over here. And all these configurations are first passed on to Ingress controller, and Nginx will proactively pull the routes, as you can see over here, so that it can implement it. So basically here we are kind of controlling Nginx from within the Kubernetes cluster, and all this comes by default with the Kubernetes in the standard way. And this is very suitable for non-RTC applications, like if we have a website or things like that, where if let's say one or two packet goes down, or packets are dropped, or service goes down for a few seconds, nothing happens. So it is very much suitable, and it is very simple, and it is also by default, so you don't have to worry about changing any of this if you are not dealing with the RTC application. But when you are dealing with RTC application, there are challenges. So what is the biggest challenge over here? So first challenge is that these Ingress controllers, they are too basic. Now all of you know that one of the most widely used protocol in the RTC is SIP, right? And you need to do a lot of routing by doing deep packet inspection. You need to look at the headers, sometimes you need to look at record routes, domains, users. There are a lot of headers in the SIP, and you have to take decisions that where a particular traffic should be routed. So I'll just give you an example. Let's say that this is an RTC application, and this is a pod dedicated to tenant A, this one is dedicated to tenant B. So now, if any packet has a domain A, then it should be routed to tenant A pod, and if any particular packet has domain B, then it should be routed to pod B. Now this is not possible with Ingress controllers because they are too basic. They can just do the routing like round robin or just load balancing, but it's not that much flexible. And some of the popular Ingress controllers that you can see, like Nginx, which I just demonstrated, HA proxy and traffic, these are the most popular ones. And like I mentioned, that all of these are suitable for HTTP, HTTPS traffic, and they are not suitable for RTC and especially SIP based applications on top of that. And I just mentioned some of the headers which we usually use in order to route the traffic or make the routing decisions. So here you go. So finally, OpenSIPS is the answer, because OpenSIPS is very good with deep packet inspection. It can look at each and every detail of a SIP packet and then it can route the traffic. So what I did over here, so here you can see this is a BGP network, right? So in this diagram, these are two pods, and this is a non-worker node or non-cluster node which is outside of the cluster. But because of this Calico based BGP cluster, they can easily talk with each other. Also what I did, that because it is part of the same BGP network, OpenSIPS can also reach to the core DNS, which means that it can just use the domains which are assigned by the Kubernetes in order to reach to the pod. So here, OpenSIPS works out of the box. Like the routing rules, as you can see, it is taken from the database. Now this database is up to you. Like you can use any kind of database and how you want to control and define the routing rules. And here, as you know, that there are capabilities of OpenSIPS, right? It can do a lot of things. It can do failovers, it can do load balancing, it can do forking. So the possibilities are totally endless over here. So here you can see that we have eliminated one more layer. Like there is no routing, as you can see in this diagram, there was an Ingress endpoint, and there is this routing rules over here, and then there is a service. We don't need any of that complexity. Okay, so as simple as that, just set up a Calico based BGP to peer network, have OpenSIPS, register OpenSIPS as a known cluster node, and that's it. Then you can do whatever that you can do today outside of the Kubernetes. Like today, what you can do, like you can just put OpenSIPS, and then there will be the tenant specific applications which will be hosted on that particular VMs, and there is no layer of Kubernetes, there is no abstraction or nothing, right? So all of you are familiar with that. So same thing and same rules now applies over here. So this simplifies the routing, the management, the failover, and it also kind of satisfies the requirement of an Ingress controller. So yeah, I think that's it for me for today. Thank you so much, all of you, for attending this presentation. And if you have any questions, like you can please add the comments. Thank you.